And today we're going to learn a new technique called power sizing model. So power sizing model, it recognizes that the cost of something varies as some level of changes in capacity or size of the project. One example is, imagine that you are building a road, okay? You're paving a road actually, and then you have some experience paving like one lane road, okay? For example, like this one, this pavement, it's just one lane. Everybody knows that, okay? This is just the intersection in front of our stadium, okay? And so that branch of the road is one lane. So imagine that if you have paved this one lane part, and then now I want you to estimate what's the cost for paving this surface, which is 2 lane. Okay, so a very simple estimation is gonna be, well, you double the 1 lane cost, right? Because 2 lanes means the size is bigger, twice bigger than the size of the 1 lane pavement. So you might want to double the cost. And another, so that's how the power sizing model work. So it tells you that there is relationship between the cost and the size. So the bigger the size, the higher the cost, right? But sometimes you might find there is the economy of scale included. Like to pave the 1 lane road, you have to rent some construction machines, paver, and workers. You deliver the material to the site, right? That's what you need to do. And then if you pave the 2 lane roads, you still have to do all the same thing. Maybe the same number of pavers, the same number of construction machines, same number of workers. You just need longer time, you just need more material, right? So the cost for you to transport those machines and people to the site stays the same, okay? Which will keep the cost for 2 lane pavement maybe much lower than the double of 1 lane pavement. You know what I mean? Because some part of the 2 lane pavement stays the same as the 1 lane pavement. That's why you have the economy of the scale. Okay, so sometimes the more you construct, the total cost or average cost will go down. Okay, and so that's a phenomenon involved in this power sizing model. All right, so let's go back to this equation. So the model says that, okay, we consider the size and we think the size make differences in the cost, okay? So there is an equation between describing the relationship between the cost, C, and the size, S, okay? So C is the cost, and CA, CB, which means we have 2 scenarios to compare. One scenario is known. I mean, CB is something, the cost of B is known. And CA is cost for plant A, CB is the cost for plant B. Or we can say project A, project B, okay? And usually, if you write the formula like this, which means CA is unknown and CB is given. Okay, and also another thing is you have to compare these 2 costs at the same time. So if you have the given cost for project B at present, then the estimated cost for project A is also at present, right? We all know that the price and the costs and money change with time, right? So you have to make sure that the comparison is done at the same time. And okay, so on the other side of this equation is the size A, size B. So SA is size of plant A, SB is size of plant B. Okay, so you are given that there are two sides of the similar plant. One is bigger, one is smaller. One is more powerful, one is less powerful. And they're all given. And another variable in this function or in this equation is x. So x is called cost capacity factor to reflect the economies of scale. Remember I said that? So sometimes you have economies of scale, like the more you build, actually the average cost is getting down. But it's not always the case. Sometimes it can be, these economies of scale. It happens when your company gets super big. Like, just imagine that if you have a bigger international corporation to produce, clothes, then if the designer wants to put up a new design, maybe change the color, change the material, then it will go through a long chain of decision making. Okay. So the material department needs to know that, the design department needs to know that, and the marketing department needs to know that, and everybody needs to be on the same page and approve that idea. So it's gonna be like a long time and a bigger cost to make this little change. That's these economies of scale. Okay, but if you just have a small company, maybe just 10 people. Okay, one person is to design, one person is to buy the material, one person is to do the advertisement. Then for your small company, if you want to change the material of a t-shirt, right? It's very quick. You just sit on the table and then discuss maybe 5 minutes, and then everybody think it's a good idea, then let's go, right? So usually in a bigger company, your economy of scale is hard to get. And the more you produce, the more design you get, the much more marginal cost you're gonna pay. So average cost will go higher. Okay, but here in this equation, what can the x is something can tell you if it's a relationship for economy of scale or diseconomy of scale, and you just need to see if x is bigger than 1 or smaller than 1. If x is smaller than 1, which means the marginal cost will decrease. Okay, and you have the economies of scale. So you want to build bigger plants. You want to pave wider roads. And if x is bigger than 1, which means the more you produce, the higher the higher marginal cost you're gonna have. Then you're gonna experience these economies of scale, and that's not what you want. Maybe build a larger plant or producing more is not a good idea. Okay, but you don't have to worry about that. It's just something additional I want you to learn from this. Okay, now let's take a look at this example. So suppose that an aircraft manufacturer desires to make a preliminary estimate of the cost of building. They want to build something, okay? They want to build a 600 MW fossil fuel plant for the assembly of its new long-distance aircraft. So they are building a new project or a site, okay, or a plant. And the size of it, sometimes we use the area as a size, or we can use the number of units as a size. And here we can use the capacity value as a size. So 600 MW is the size of this new plant, okay? And it is known that a 200 MW plant cost 100 million 20 years ago. Wow, this is tricky. Okay, so many information in this sentence. it is known that 200 MW plant, that's another plant with a lower capacity or lower level of power, okay? And the size is 200 compared to the new plant whose size is 600, okay? And the cost of this smaller plant is 100 million, but the price is 20 years ago, okay? Keep in mind the time stamp, it's 20 years ago. So, let's just write down the given condition here, okay? So, seems like we know the price of the smaller plant. Like what we said, okay, CA over CB, we just wanna, copy this formula first. And actually the formula, we have two forms, and then I would like to use the second form a lot, because that will give you the unknown variable CA on the left side and moves everything to the right side, okay? So CA, let's write it here actually. CA, that's the unknown cost. Remember that is CB times size what? Size A over size B to the power of X. That's your equation. Okay, and we said that the CA is the unknown cost, so CA must be the cost of this. So in this example, the CA is unknown cost, and we know that the cost we want to know is about the 600 MW fossil fuel plant, okay? So CA is for this new plant, and CB is the known or the given plant cost, which is related to this smaller plant, 200 MW plant. One thing we need to know is that the cost of 100 million is the cost 20 years ago for the smaller plant. So we need to think about how to convert that old price to the current price. Because of course, if you want to build something new, you want to know the price for now, right? And SA is the size of the unknown plant, which we said is 600. And the size B is gonna be the size of the plant for comparison, so which is the 200. Okay. And let's continue to read the statement. So it is known that a 200 MW plant cost 100 million 20 years ago when the approximate cost index was 400. So this cost index is actually the I bar, right? But it's 20 years ago. 20 years ago. Well, we don't know which year it is. We just label it as 20 years ago, okay? So we know that the index is 400. And that cost index is now 1,200. Okay, so from this we know the I bar now is 1,200. So if you know the two indices at the 2 years, okay, and then you also know the price for one of the years, so it's easy to calculate the price for the other year. So we will use the indexing method first to convert the price for the smaller plant 20 years ago to now. And then we're going to use the power sizing equation to calculate the cost for this new plant. So that's the logic. And the very last sentence tells you the cost capacity, which is the X, is 0.79. Okay, so this is all we know. And we said the first step, step 1, we want to calculate the current price or cost of the smaller plant, which is the 200 MW plant, right? And step 2, we want to use power sizing method to calculate the CA, which is, the 600 MW fossil fuel plant. Okay, so let's do the first step. Step 1. All right, so for step 1, we need to first copy the equation here. The index method, the equation is Cn is Ck times I bar n over I bar k, right? And we know that the n is what year is now, okay? So that's something unknown. And we also know that k is gonna be 20 years ago. That's just a year time, okay, compared to the year now. And so the Cn is the C now, but we have to keep in mind all of this is about the plant B, which is the 200 MW plant, okay? So all of this price is for this smaller plant. Okay, so according to this equation, we know the C now is the C for 20 years ago times I bar n is now, so I bar now over I bar 20 years ago. Okay, so replace this with the variables. The price for the 200 MW plant 20 years ago is 100 million. And the I bar now is 1200. The I bar 20 years ago is 400. So the two indices tells you the price for now for this smaller plant is 3 times the price 20 years ago. Okay, so now the price is 300 million US dollars for the smaller plant. Okay, so we know that the CB, because we said CB is the cost we know, and that's the cost we just calculated. It's 300 million for now. So this is our new CB. Okay. So step 2, this is step 1. And then let's change the color. And let's do step 2. Is to use the power sizing function, okay? That function is CA is CB times SA over SB to the power of X. And here we said plant A is something unknown, so that's our 600 MW plant. And the size for A is 600. So plant B is related to our smaller capacity plant, and the size B is 200. And X is 0.79. Okay, so CA is the cost we want to know. CA is the cost of the 600 MW plant. So CA is CB. So CB we already know it's here. Okay, so CB is 300 million US dollars times SA is 600, SB is 200, and X is 0.79. That's the power of this ratio. So it is, the final result is 714 million. Okay, so it tells you that the cost for this 600 MW fossil fuel plant is gonna be 740 million US dollars for now.